Welcome to the fifth lecture on my series on thermodynamics. In previous lectures, we have met the zeroth law and understood how that leads to the concept of existence of temperature. Now, the very end of the first lecture in this series, I had given a summary, a rather tongue-in-cheek summary of the basic laws of thermodynamics. And there, I had said that the first law essentially says that you can't win. What it really means is that you can't get energy for free. Energy is something which is conserved. So before we start talking about the first law in earnest, we have to recapitulate some notions about at least one entity which is deeply connected to the concept of energy, at least to the way in which energy is either accrued or depleted from a system, and that is the concept of work. Now, work is actually a pre-thermodynamic concept. It's a concept which comes from subjects which are studied before thermodynamics. So, you are supposed to know about work even before your first class in thermodynamics. The origin of that notion is really in mechanics. However, the concept that we use in thermodynamics is a bit more general. In mechanics, of course, we say that work is done whenever a force makes a body move. Or, what is the same thing in a different form, a torque makes a body rotate. However, in thermodynamics, any exchange of energy that a system can do with its surroundings while being enclosed by adiabatic walls is characterized as work. Of course, that doesn't mean that if the walls were not adiabatic, you would not be able to do work. It only means that if the walls are diathermal, non-adiabatic, then there can be other means of exchanging energy in addition to doing work. Now, even for a given system, if we just confine ourselves to the means of doing work, there could be several different modes by which it could be done. We will focus primarily on what are called simple systems. A simple system is one in which there is only one means of doing work. We will sometimes talk about systems which are not simple, complex systems, but that will be a rarity. Now, among the simple systems, the one that we will deal with most often in thermodynamics is actually called a hydrostatic system. Is one in which the state can be completely specified by its pressure P, volume V, and amount N. Amount here means number of moles. Now the reason why these kind of systems are called hydrostatic systems is pretty straightforward. The most common example of these systems come from fluids, liquids or gases. And in a hydrostatic system, the means of doing work is purely mechanical. It's force times displacement. So you don't have to worry about any other kind of energy exchange in order to talk about hydrostatic systems. Now, because mechanical work is going to play an important role, at least in establishing the kinds of things that we are going to call work in thermodynamics, let me quickly give you a recap of work in mechanics. Now, for a point particle, the work done is defined to be simply the line integral of force dotted with displacement over the path taken. And the reason why this is an important quantity in mechanics is that the work energy theorem equates this net work done by all forces acting on a point particle to the increase in its kinetic energy. Now, one very important point is this work done is usually path dependent. If you go from point A to point B via two different paths, the amount of work done by the same force in the two cases may very well be very different. However, there are special kinds of forces called conservative forces for which the work done is independent of the path. And as you definitely recall from mechanics, for such forces where the work done is independent of the path, you can define the concept of a potential energy. And these concepts can all be extended to systems of particles. So when we talk of energy and work in thermodynamics, we are essentially borrowing these kinds of ideas, although within classical thermodynamics we are going to treat the system as a whole and not worry about the point particles or atoms and molecules which make up the system. But the basic idea is still more or less the same. If you do work on a system, its energy goes up. Now, in a hydrostatic system, as I've already said, the work done is purely mechanical. And in this case, work is done when a hydrostatic system, which remember is described only by P, V and N, pressure, volume and amount of substance. Here work is done only when it changes its volume. And this is purely mechanical, as we have already stated. Let us take a look at what we are talking about here. Consider gas enclosed in a container. The gas is here and the container has a movable wall. Now, you are exerting a pressure from the outside, the P external, and also there could be frictional force between the wall of the cylinder and this particular movable wall. In this case, the net external force which is acting on the gas will be that due to the pressure, which is of course the pressure times the area. Area A here is a cross-sectional area of the piston, to which you have to add the frictional force, which is also acting in the same direction, that is against expansion. At least, if the gas were expanding. Now, what is the net work done by the gas when it expands and this wall, the movable one, shifts to a distance delta x? According to standard mechanics, when the gas expands, it has to do work against the external force. It has to produce force on its own and it has to do work against that. Or you could say the external forces do negative work on the gas. Now this work done by the gas is simply the product of the force with the displacement. In general, it should have been a dot product of the force with the displacement, but here the force and displacement are in the same direction. So you can get away by just multiplying the two together. Now, if you look at the two terms here, you have P external A times delta x, where I have deliberately put A delta x inside a bracket. Plus, of course, you have F frictional times delta x. And the reason why I put A delta x in a bracket is pretty clear. A being this cross-sectional area, when it has shifted by delta x, A times delta x is simply the increase in volume of the gas. So P external times the increase in volume of the gas, plus of course the work done against the frictional force, which is F frictional times delta x. Now if you have a smooth piston here, F frictional would be 0. So work done by the gas, which of course is actually negative of the work done on the gas by the external force, is P external times delta V. Note that if the system expands, that is delta V is positive, it has to do work against the external pressure. So work done by the system in this case will be positive if delta V is positive. Of course, if the system contracts and delta V is negative, the system actually gets work done on it by the external forces. But you don't have to change the formula for work done by the system in this case at all, because here delta V being negative, the gas having contracted, P external times delta V will come out to be negative, which is fine, because when work is done on the gas, it's actually negative work done by the system. Because when work is done on the system, in this case the gas, It's actually the same thing as negative work done by the system. Now, one very special kind of situation that we will talk about very, very often is what is called a quasi-static situation. In a quasi-static situation, changes occur very, very slowly, so that at any given point in between the system transiting from one state to another, it stays very, very close to corresponding equilibrium states. Now, in this situation, where you have a gas which is exerting pressure on a piston from the inside, and there is an external pressure acting on the piston, such a quasi-static process is possible, assuming, of course, that there is no friction, which is something we have already assumed, is if the two pressures balance each other out. Of course, if they were to exactly balance each other out, the wall would not move at all. So we could think of a situation where if the gas were expanding, the pressure internally would be infinitesimally bigger than the external pressure. If it were the other way around, that is, the external pressure were infinitesimally bigger than the internal pressure, the gas would very, very slowly contract. So we can say that for such a process, a quasi-static process, pressure of the gas P is actually equal to the external pressure. Let me remind you that we have taken the frictional force to be 0 for this. And under such conditions, we get work done by the gas is simply P times delta V, where P and V both refer to the thermodynamic coordinates of the gas itself. P here, in this version of the formula, is the pressure of the gas, and V, of course, is the volume of the gas. Note that this is not the situation in general. It's the external pressure times delta V which is actually the work done if frictional forces are not present. But in the case of quasi-static processes, as we have just explained, the difference between P and P external is negligibly small, and so the work done by the gas in this case will be P delta V. This is perhaps an appropriate point to talk a bit about the convention that we are using here. Now, some thermodynamics texts refer to work done by the system, and that, as we have already said, is P times delta V. Whereas some other thermodynamics texts actually talk about work done on the system. And there, W is actually the negative of this particular W. So it works out with minus P delta V. Now, whether you are going to talk about work done by the system or work done on the system, this is merely a matter of convention. And as long as you consistently follow any one of them, things will be perfectly fine. The trouble is, many textbooks use either convention depending on the situation that we are in. The problem is, many textbooks actually switch from one convention to another depending strongly on what kind of situation they are dealing with. And some do not even signal that they are actually making a change. And all this becomes very confusing to students. I would advise people to follow only one of the two conventions and not mix them up, because that will lead to a lot less confusion in the long run. However, it is pretty easy to actually switch from one convention to another if the need be, especially if you're reading a textbook which is using a different convention. Just think about whether the work done is positive or negative when the system expands. When it expands, delta V is positive. So P delta V will turn out to be positive. And so if P delta V is the formula which you are using for work done, then you are actually talking about work done by the system, because that is what is positive when the system expands. It expands against external pressure, so it has to do work in that case. On the other hand, if you are talking about work done on the system, you're really talking about the external forces doing work on it, and that happens when the system contracts, because then the wall, for example, gets displaced in the same direction as the external forces. So whether it's plus P delta V or minus P delta V, that depends on whether you're talking about work done by or work done on the system. Once again, just stick to one consistently and you will never land in trouble. We are going to use work done by the system almost throughout this course, if sometimes some things are better explained if we talk about work done on the system, I might switch to that, but then I will clearly tell you, as long as I remember to, where I am making the switch. If I don't say anything, you will always have to assume that I am talking about work done by the system. Now, it's very often convenient to describe processes that occur in systems by a geometrical or graphical representation. And in order to do that, we need to first have a proper idea about what we can call the thermodynamic state space. There is a geometrical space which describes all the equilibrium states of a system. Note that equilibrium states of a macroscopic system can be characterized by a rather small number of thermodynamic coordinates, so you can think of each state as a point in a suitable low-dimensional space. In particular, if we are going to talk about a hydrostatic system, which is characterized typically by, say, the pressure, the volume, and the number of moles, this thermodynamic state space is a three-dimensional space. So if we, say, plot pressure along one axis, volume along another, and number of moles along a third axis, then we can draw a 3D graph, and points on that 3D graph will correspond to each equilibrium state. Now, 3D graphs are not really that convenient to draw or visualize, but what makes our life a lot simpler is that very often the kind of systems we are dealing with are systems where the number of moles of the system, the amount of material, is fixed. So if we focus, at least for the time being, on such systems with fixed n, then the equilibrium state of a hydrostatic system basically becomes a point in a two-dimensional space. A 2D space which is characterized perhaps by the pressure and the volume as coordinates. And we can, of course, plot the states of such a system as points on what is called a PV diagram. This is also called an indicator diagram. A typical PV diagram, which just shows a few points or few states depicted as points, is shown here. You have the point P1, V1, which has pressure P1, volume V1, the point P2, V2, pressure P2, volume V2, and so on. Now, we would use such diagrams not only to depict equilibrium states, but also processes in which a state changes to another. A process, of course, can be denoted by indicating its initial state and its final state, but that, of course, does not tell you about what's happening in between. And frankly, the situation in between is something that we cannot usually show on an indicator diagram. Note that the points that we have on these diagrams all correspond to equilibrium states of the system. If the state of the system is changing, say from PIVI to PFVF, from an initial state to a final state, the states in between are not necessarily equilibrium states. Usually they are never equilibrium states, and that is why the system changes from one state to another. However, very often what we do is consider quasi-static processes. As we have already stated before, in a quasi-static process, the system is not really in equilibrium when the process is occurring, but even when the process is occurring, at any given instant, it is arbitrarily or infinitesimally close to an equilibrium state. So, I can, in such a situation, indicate the process by drawing a continuous curve on the PV diagram, where each intermediate points on the curve are actually points which are very, very close to the actual state of the system. The points on the curve are, of course, equilibrium states, but in a quasi-static process, our system goes very, very close to these intermediate states. And so, quasi-static processes can be denoted by a path in the indicator diagram, as opposed to a general process, which can at best be shown by the initial point and the final point, And usually when we want to indicate such a non-quasi-static process, we plot the initial point and the final point and draw maybe a broken line joining the two to indicate that some process is happening in between, but we cannot actually indicate the states of the system as the process is occurring by points on this diagram. Now, as we have noted above, the work done by a gas under quasi-static conditions is given by P times delta V. P here being the thermodynamic pressure of the gas and V of course being its volume. This will be valid as long as P is a constant. But if P changes, what we need to do is to use this formula for very small parts of the process, and in each of these small parts, the work done is going to be P times the infinitesimal change in volume, and you have to add them all together. So P dV has to be integrated to get the work in this case instead of P delta V. And it's easy to see from class 12 level calculus that in a simple hydrostatic system where the work done is P dV, the work is simply the area under the PV curve. Note that this works only for quasi-static processes. Only for quasi-static processes can we actually draw a curve on the PV diagram which indicates the process. Now, from this geometrical interpretation of the work done, it's pretty obvious that if I went from the point PIVI to the point PFVF via various different quasi-static processes with different paths as indicated on this picture here, the work done will be different in each case, simply because the area under each of these curves is definitely different. Now, because of this, we do not actually write PdV, this infinitesimal work done, as dW. We put a cross on the W. So we write D, but there's a cross here. The cross on the D cross indicates that this is not really an exact differential. What that means is that there is no function of the thermodynamic coordinates whose differential actually gives you the work done for a general infinitesimal process. Note, if there did exist a function W, then the infinitesimal work done for a small part of the path would have been dW, and then if you were to integrate dW along any path which goes from PIVI to PFVF, would simply have been W at the end minus W at the beginning, which is something which follows simply from the fundamental theorem of integral calculus. If you have a differential of a function which is being integrated, then the definite integral is simply the value of this function at the end minus the value of this function at the beginning. And this is definitely independent of the path taken, because this expression depends only on the final and the initial points. This is why we are so sure that here you cannot have a W whose differential PdV is, and in general work done is always path dependent except under very special situations. And therefore the infinitesimal work done is written down with D cross W and not dW. Now in our case, for the hydrostatic system, D cross W is PdV, and it's easy to check that this is not an exact differential. Had it been an exact differential, had there been a function W whose differential this is, then PdV would have been dW, but dW, as we know from multivariable calculus, is simply partial derivative of W, which is P, at constant V, dP. So this is the part of the change in W which happens because the pressure is changing, and this is the part which happens because volume is changing. Del W del V at constant P dV. Now in our case, equating this expression to PdV would give you two results. Del W del V at constant P would be simply P, the coefficient of dV on this side, and because there is no coefficient of dP on this side, del W del P at constant V would be simply 0. However, this one would simply tell you that if I were to differentiate then with respect to V at constant P, I will get the mixed partial derivative del to W del V del P, which is equal to 0. And if you were to try the same thing here, but differentiate with respect to P partially, you will get the mixed partial derivative del to W del P del V, and that would work out to be 1. Now this is the contradiction to a basic mathematical result. For any function which is smooth and has continuous partial derivatives up to the second order, the mixed partial derivatives has to be the same. Del to W del V del P must be equal to del to W del P del V. This, of course, is a contradiction here because that would have said 0 equals 1, which we know cannot be true. This contradiction actually shows you that you cannot have a function W whose differential will be PdV. In fact, because we are going to need this later, let me point out that if your function phi is a function of many variables, x1, x2 up to xn, and if d phi is an exact differential, that is, there is really a function phi whose differential we are talking about, with f1 dx1 plus f2 dx2 plus f3 dx3 up to fn dxn being its expression, then fi, the ith coefficient, is actually del phi del xi. And so if you were to do del fi del xj, then that will actually be equal to del 2 phi del xj del xi. But that, according to the theorem that I just quoted, must be equal to del 2 phi del xi del xj, which means del xi of del phi del xj, and del phi del xj is fj. So you must have del fi del xj equals del fj del xi. If this does not happen, it's impossible to find a function phi whose differential will give me f1 dx1 plus f2 dx2 up to fn dxn. By the way, this particular condition, del fi del xj equals del fj del xi, has to occur for all I and j, each and every pair. And also, we must realize that what we have written down here is a necessary condition for f1 dx1 up to fn dxn to be an exact differential. We usually consider this to be sufficient, but that is really not perfectly true. It does work out in all cases of interest for us. Let me stress once again that work done is in general path dependent. Not only is PdV work done, the kind of work that is done in hydrostatic systems, path dependent, other kinds of work done is also path dependent in general. However, there is a very important special case where the net work done on a system depends only on the initial and the final points and not on the path taken. So, in such a situation, the work done is no longer an inexact differential, but rather is given by an exact differential. This is going to be the main topic of our next lecture, where we are going to introduce what the actual form of the first law of thermodynamics really is. Until then, goodbye.